American Meteorological Society's policy program is supported, in part, by a public-private partnership.
Our next speaker is Nick Keener. He's the Director of Meteorology for Duke Energy Corporation. His responsibilities include directing a team of 11 meteorologists and scientists in providing weather forecasts to support Duke Energy's operations and planning. Mr. Keener is a certified consulting meteorologist, serves on the board of the National Council of Industrial Meteorologists, and is active on the National Academy of Sciences Board of Atmospheric Science and Climate. So this one's the pointer button.
This one's point, and this is forward.
This is advancing.
Okay, good. Well, I've been in the utility industry for 34 years and also a meteorologist for that long. And one thing I will mention in Mark's discussion is that no one remembers the forecast you get right. They always remember the forecast that you miss. And as I tell young people going in the field of meteorology, that you're going to have thick skin to go in this line of work, believe me. Let me introduce a little bit about what Duke Energy Corporation is and kind of diversification in terms of what we do. We're a very weather-impacted business, the energy sector, particularly the utility sector, and I'll discuss that in more detail. We have, in terms of the regulated operations at Duke Energy, we operate in 6 states. We have a commercial business sector that operates renewable energy across the U.S. in terms of wind and solar. And we also have international operations, primarily hydro. I think about 3/4 of it's hydro in Latin America. Basically, our generation portfolio in the regulated parts of our business is coal, 38%, natural gas, 38%, nuclear, 17%, and hydro renewables, 7%. The hydro, or particularly renewables, is the one that's growing quite a bit and growing very fast. The states that we operate in, from Florida to the Carolinas to the Midwest. In this particular slide, things to note that we serve 7.3 million retail electric customers across these regulated jurisdictions, and about 500,000 natural gas customers across those as well. Renewable energy, we have about 1,800 megawatts of wind and solar in 12 states. We have pipeline projects, and we have a growing wind and solar business. In international operations, particularly in the Latin America, primarily hydro, and that's one of the things I'm going to talk about in terms of the utilization of seasonal forecasts. It really impacts hydro operations. Daily to seasonal operational uses, as you know, when it's warm outside, you turn on the air conditioner. When it's cold outside, you crank up the heat. Electric utilities make money when you crank up the heat and crank up the air conditioner. So obviously, knowledge of what the day-to-day, hour-to-hour variability in weather is very important to determining how we're going to fire and optimize our generation portfolio. Also, seasonal forecasts, 2 weeks going out to several months, is also important in terms of how we operate our energy portfolio. Generation dispatch and load forecasting is simple as temperature forecast, wind forecast, dew point forecast goes into models which generate how many megawatt hours of generation you're going to need to generate. We've looked at studies. Even if you increase or decrease the error in temperature forecasts, even a half a degree, you're looking at millions of dollars of savings annually in terms of generation dispatch. So just incremental improvements in just the temperature forecast on an hour-to-hour basis has tremendous in terms of saving and reducing your generation errors. Precipitation forecast, which I'll talk to in a little bit more detail, is extremely important, not just on the day-to-day amount of precipitation that's falling across a particular hydro basin, but on seasonal forecasts, which we've been incorporating in terms of our hydro operations, particularly in the Carolinas, for a number of years now. Renewables, wind and solar, as we see more renewables on the grid, particularly wind and solar as well. The day-to-day variability in terms of wind and solar is increasingly important in terms of generating or optimizing your generation portfolio. Obviously, knowing what the wind resources and what the prediction of the solar amount of radiance forecast and how it may deviate from climatology on a year-to-year basis and become increasingly important as you see more solar on the grid. Fuel supply, obviously, in terms of optimization, depending on the seasonal forecast, if you're going to have a hotter summer or a colder winter, you're going to make long-term positions in terms of how you optimize your fuel in terms of buying gas, oil, and looking at in terms of your how you generate or how you schedule your large generation outages. Storm prediction and resource modeling for storm impacts is also important in utility operations. Whether you're going to have a more active hurricane season, more active season in terms of potential ice storms, snowstorms, or dry conditions is important in determining what the resource needs and what the supply chain in terms of amount of poles, conductor, transformers you may need for severe weather. Extreme weather impacts to generation for planning and maintenance, transmission line, high bill analysis, earnings or weather adjusted earnings is very important. Monthly and seasonal forecast for system planning and thermal modeling, just to name a few. I'm going to bring up this U.S. Drought Monitor, and I'm going to look at two cases. This was, let's see if I can get the, I'm not going to do a pointer here. Let's try, if you look at the southeastern U.S., this is December 2004. We were in the significant drought conditions during that period in the Carolinas portion of our service area, and we have quite a bit of hydroelectric in the western part of the state. And you contrast that into 2003 was a relatively wet period across that area. So if you look at just in terms of generation or rainfall variation and generation across our Catawba Basin, which that's a river basin in western North and South Carolina, it has about 2,500 megawatts of hydro along 8 hydroelectric stations. You can see a difference between 2007, 2003, and 2007. Well, that delta in megawatts turns out to be about a little over $50 million. So as you can see, it's important in terms of looking out ahead from a seasonal standpoint of what the precipitation is going to look like in the patterns going through a spring and a summer in terms of how our hydroelectric system operates. Obviously, if we're going into a period of dry conditions, normally La Ninas, which is the opposite of El Nino, tend to result in a little bit drier conditions across the southeast. Normally, once we see that, we start ramping back and conserving our water resources, so we have more water available for hydroelectric generation, but we also have more water available for all the people that utilize those reservoirs across the system, including those that are pulling out, and municipalities are pulling out drinking water. So it becomes extremely important, not just for hydroelectric, but also operation of the entire basin to make sure everybody has water. And I think that's one of the big utilizations in seasonal forecast right now, and I think it has even more importance in terms of how we go forward in terms of both energy and our economy, in terms of water resources. Just give you another idea on renewables. Seasonal weather trends is important for renewable energy, particularly wind and solar. If you're going to have a potential for a period of more variability, more cloud conditions, you can reduce the amount of solar generation you may have in a grid where you have solar generation. Same thing with in terms of wind as well as hydro. And I want to show you this was out of Bloomberg magazine. And as you've heard, the drought and the very warm temperatures we've had across the western U.S. There's a lot of wind resources and wind power out in the western U.S., and California in particular has a lot of wind generation coming into its ISO. And as you can see, if you compare June 2015 to June 2014, you see that there's over 1,000, about 1,500 megawatts of reduced wind energy coming into California. And that's a direct result of the ridge across that region resulting in drought conditions. So to get an idea, being able to forecast that in advance from a seasonal operation standpoint can let generation planners, independent system operators, and utilities make decisions in terms of their generation portfolio and whether they need to import power, secure more power. They may have to buy gas to make sure they have additional energy to get across peaking, with the expectation there may be fewer wind resources. I can see the same in solar as well as we get more solar across the grid in the U.S. This is just an idea on seasonal forecast and seasonal hurricane variation. As you can see, during a warm phase and during a cold phase, and that's the AMO, but you can see areas in seasonal periods where you do have a higher frequency of hurricanes and lower frequency of hurricanes. And essentially what that means is not so much if, whether I have beach property and I want to put in bigger shutters, going to have a better chance of a hurricane. But essentially, utilities will take a look at the seasonal forecast for hurricanes and make a determination on their supply chain needs for going into that summer. For example, we have operations in Florida and the Eastern Carolinas, which are particularly North Carolina, is very susceptible to hurricanes. So one of the things we do is we look at the seasonal forecast in terms of hurricanes, and we take a look at whether we are stocked well with transformers, poles, and things of that nature to ensure that we have those supply on hand to ensure that we can go ahead and restore power if we do have a major storm. Ice storms is another forecast problem, and I've always said the biggest disruptive weather event you can have is ice. Ice will really tear a grid up, and some of the things we utilize forecasts for in terms of seasonal is to look at if we have a potential for more ice events during the winter months. Going into an El Nino period usually gives us a little bit more wetter weather in the southeast, which results in a little bit higher instance of ice storms across the southeastern U.S. So we'll take that in consideration during planning. Wanted to look at extreme cold and extreme heat, and one of the uses of seasonal forecast is to take a look at, for example, as you go in the last two winters, we had the phenomena, the so-called polar vortex, where we had a very strong trough developed in the winter months, which injected very cold Arctic air across the eastern and Midwest parts of the U.S., and that resulted in very, very cold conditions. So one of the things we try to do to looking at seasonal forecasts is determine what that seasonal variability in terms of temperature, where we have a number of extreme cold or extreme heat events, whether it's winter or summer, and then take a look at how we prepare our generation stations to perform for very cold conditions, very warm conditions, but also look at our optimization of how we schedule our large generation resources. So, for example, we don't want a 1,100 megawatt nuclear unit going offline in February. If we think that the risk in February is greater for extreme cold, we may want to make sure it goes off early March instead of late February to reduce the risk. Because if that 1,100 megawatt generating station goes off, we're going to spend a lot more on securing energy, whether it's on the spot market for gas, or which will be much higher at that time, or other generation resources. Same thing, as I said, with maximum temperature probabilities. We try to look at from season to season how the seasonal forecast and what we're looking at in terms of analog years. As we go into a summer season, do we expect more periods of extreme heat or more periods of 90 degree or 95 degree plus weather, and how we look at in terms of scheduling our large generation units to be off. It becomes very, very important in a scheduling and resource optimization. And that's it.